we can start with this relation, like voltage and current relation of uh, uh, voltage and current relation in these elements, like a resistor, inductor, and capacitor. So if you observe this table here, so voltage and current. So I hope now we are familiar with what do you mean by voltage, what do you mean by current. Okay. So already we have discussed about this resistor, inductor, and capacitor, right? So what are these elements, what is the property of these elements, how it behaves, what are its properties as well, how it behaves when we supply voltage, and what is the current flow through that element, and how the energies are being stored, or how the yeah, so how the energies are being stored in, especially in the inductor and as well as the capacitor. But whereas coming for the resistor, it absorbs energy in the form of heat. So because, and moreover, so resistor is also called as the unity power factor load. So I can call it as unity power factor load. So let me discuss later on what do you mean by power factor. Okay. And coming for this inductor, this load is called as a lagging load. So resistor can be called as the unity power factor load, and inductor, which is denoted by L, can be considered as the lagging load, and the capacitor C, so it is called as the leading load. So why we are calling it as lagging or leading, especially because based upon this voltage and current relation. So in the inductor, already we have seen in the previous class. So soon after, when we are supplying the voltage for this inductor, so the current starts after 90 degrees in case of ideal conditions. Okay. Other than ideal condition, in the sense it will be less than 90 degrees. Let me show you the graph. So this is what, right? So for this inductor, when we supply voltage, so this indicates the voltage there. So when the voltage is supplied, what happens to the current? So after 90 degrees of after 90 degrees of time period, the current starts flowing through this inductor. Okay. Yeah, right. So this is in ideal case. So this difference is 90 degrees only at the ideal conditions, but all the time there will not be any ideal conditions there. It will be always less than 90 degrees. Okay. So that is why current lags the voltage in case of inductor. So that is the behavior. And coming for this capacitor, so let me draw you. In case of capacitor, suppose this is the applied voltage. So this is the voltage applied across the capacitor. So the current will be leading there. So this is the current, and this is the voltage. So here the I leads V. So hence it is called as a leading power factor load, or leading load. Sometimes you can call it as a leading load as well. Okay. So there, that is the reason for calling these type of loads. Okay. So in terms of equation, so let us write in terms of equation. See, V equal to IR. So as per Ohm's law, again. So because of its linear behavior, already this one also we have discussed in the previous session. So it obeys Ohm's law. So that too under constant temperature conditions. Okay. So here, so V is proportional to I in case of resistor. So and hence it absorbs energy in the form of heat. Okay. So there is this is fine. Okay. And coming for this voltage across an inductor, so voltage across inductor, so V equal to L into di by dt. So with this equation, what we can define, so rate of change of current with respect to time. So why here it is happening? So let us see. So this is an inductor. Yes. So when we apply voltage across this inductor, so the energy stored in the inductor is in the form of electromagnetic field. So it stores the energy in the form of magnetic field. So if there is rate of change of flux with respect to time, if there is rate of change of flux with respect to time, so when it happens, when there is rate of change of current with respect to time, okay, so then only it stores energy in the form of magnetic field. Otherwise, so d by dt of constant is 0. I mean here, if there is the flux remains constant, so flux remains constant in the sense if the current remains constant. So when it happens in case of DC, so let me explain in detail about this DC supply and AC supply. So just for now, you can just remember that the voltage across inductor is L into di by dt. So if there is rate of change of current with respect to time, it doesn't mean that all the time it should be the current should be varied with respect to time, but if the current remains zero, suppose if current is zero, entire the voltage will be zero. Suppose if there is no change of current with respect to time, so it what happens? It also remains zero there. Okay. So yeah. So d by dt of constant is one. Sorry. So V equal to voltage applied across inductor equal to L. So this will not happen. So definitely, so there should be rate of change of current with respect to time. Right. So let me clear this. Yeah. And coming for this capacitor. So now let us see the voltage and current relation in the capacitor. So V equal to 1 by C integral I dt. So for easy understanding, you can use this relation V equal to voltage across capacitor equal to 1 by C integral I dt. So here we can neglect this equation there. So this is actually the initial condition. This is initial condition. Okay. So this voltage applied across a capacitor equal to 1 by C integral I dt. You can write this equation here. So where C represents the value of the capacitor, which is represented in farads. Okay, I is the current flowing through that capacitor with respect to, I mean, into time. Okay, so and here V of T naught, actually T naught represents the initial time conditions. So for time being, we can neglect this. We can make it as 0 there. Okay, so when we discuss in detail of the subject, then we can include these initial conditions. Okay, so because why here it is being given is, if there is any initial charge in the capacitor, then again the energy stored in the capacitor will be deferred. So we already know the voltage across the capacitor is, so let it be C. So if the voltage applied across the capacitor is equal to, this is the equation, so 1 by C integral I dt. If suppose there is initially charge, so before that, is there any kind of energy stored in this capacitor in the form of electrostatic field, so then again the value changes. Okay, so that is a relation. And from these equations only these are identified there. See, I equal to V by R. From this equation only it is obtained. And coming for this current through the inductor, so we should call it as current through the inductor and voltage across the capacitor. In the similar way, voltage across the capacitor and current through the inductor. Okay, so here I equal to 1 by L integral V dt. So in similar way, here also we can write I equal to 1 by L integral V dt. So again neglect about these initial conditions. Okay, so but we should consider it, since it is our first class, you can write, I mean for the first session, so 1 by L integral V into dt. So this equation you can use current through the inductor. So next, if we shift this derivative here, it will come as integration. Okay, and in the similar way, I equal to C into dV by dt. Okay, yes. So yeah, if you see here, so V voltage across inductor is L into di by dt. Current through capacitor is I equal to C into dV by dt. So from this easily you can remember the relations of voltage and current in a inductor and capacitor. So okay, next, another important relation is power and energy. So let us consider only for power right now. P equal to I square R or V square by R. So the power equal to I square R or V square by R. So where I represents the current flowing through the resistor, R represents the resistor value, or another equation also we can use for this resistor, that is V square by R. So this is applied if we include I equal to V by R. So then this equation comes. If we substitute I equal to V by R, then this relation comes. Okay, and what about this power in the inductor? Half Li square, and here it is half CV square. Okay, and these two I can explain later. So when resistors are connected in series, when resistors are connected in parallel. So separate session I will take on this and I can explain you clearly. So, but as of now, if you want to see this equation, see when two resistors are connected in series, so the equivalent resistance is R1 plus R2. If two resistors are connected in series, then the equivalent resistance is R1 plus R2. In the similar way, when the two resistors are connected in parallel, so later on I'll again give you the some more information about how we can identify it as a series or how we can identify it as a parallel. So in the coming sessions I'll give you the detailed information. See, just for time being, see, when two resistors are connected in series, the equivalent is R1 plus R2. When two resistors are connected in parallel, R1 R2 by R1 plus R2. So there we can find out the equivalent resistance, R equivalent in the sense the equivalent resistance. In a similar way, when the two inductors are connected in series, the resultant is L1 plus L2. We need to go for summation. We need to cascade it. Okay. Next, when the inductors, two inductors, this formula is applicable only if there are two elements. So especially the inductor. Here also, if there are two resistors, if there are two capacitors. Okay, so then this formula will work out. So L1 L2 by L1 plus L2. Actually, we can solve it by applying KVL there. So that is why I'm not giving you the a detailed explanation. And coming for this capacitor, see, coming for this capacitor, capacitors are if two capacitors are connected in series, then we have to multiply. So it will not get added there. So C1 C2 by C1 plus C2. So this equation we need to remember. If two capacitors are connected in series, the equivalent is C1 C2 by C1 plus C2. So we are not going to add the capacitor values. Okay, when capacitors are connected in parallel, then we have to add this. So this is the only difference between capacitor and resistor inductor. Okay, all right. So coming for this DC excitation, so again here, if the current remains constant, the value of, so the value becomes 0. So see, d by dt of constant is 0. So hence the voltage is becoming 0. If voltage is 0, so we call it as short circuit. If current is 0, we call it as open circuit. So we know that if the circuit is open, there is no flow of current. Obviously, the current value becomes 0. If the circuit is closed, I mean without any resistance or without any impedance there, without any value there, so then the voltage is 0. Let us consider a switch. I think with this example you can have some more information. Let us consider a switch. Yeah, so if we close the switch, what happens? The voltage across the switch is 0, and the current will be maximum, right? If we open the switch, what happens? The current is 0 and the voltage will be maximum. So same, here only we can apply the same here for understanding. Okay, so later on we'll see the remaining. Next, coming for this DC power. Coming to this DC power. So this is also one of the active elements. So already we have discussed in the previous session. So two sources are there, voltage source and current source. So based upon this, again these two sources we can define about power. Already we have discussed, and again in this power two classifications, that is DC power and AC power are there. So we'll discuss about this DC power. So what do you mean by DC? So it is an see, for your understanding, I can call it as direct component. Instead of calling it as direct current, I can call it as, see, sorry. So direct current. Actually, DC current in the sense direct current. So it doesn't mean that. Actually, it is direct component and alternating component. If suppose it is AC, we can term it as alternating component. So component in the sense actually the signal there, right? Okay. So let us see the statement. So DC current refers to a current formed by electrons flowing continuously in one direction. So there is, see, if the direction of current is in this way, let us consider this is a material. Okay. So if the direction of current is in this way, the electron flow will be in opposite direction. Of course. So the same, I mean, the behavior will be same even if we apply AC power or DC power, but there will not be any change of current. So what I can say, di by dt will not be there. So the current remains constant here. Okay. So at any period, time period, see if you observe this graph, let me change. Yes. See, if we look at this graph, so with respect to time period, with even though with increase in the time period, the magnitude remains same. So the voltage across, I mean the source remains same. Suppose we can call it as Vm, the maximum voltage. So it remains constant throughout the time period. So this is what actually the DC means. Okay, so constant DC. So this is the way of representation. So or we can call it as a regulated DC. So let us skip this term, regulated DC. So this is the actual DC we require. Okay. As the electrons flow through various components in the circuit, they lost their electrical energy. So that is nothing but the voltage drop. Okay. So all the time we cannot maintain a constant DC because there will be a energy loss. So DC power refers to the amount of energy dissipated per second by a coulomb of electrons. Okay. So they travel between the 2 points. Actually, the potential difference. So already we have discussed at the time of atom, right? Next, if the DC current is steady, then the power dissipated by the component will also be nearly constant. But all the time it will not be constant, but nearly, in the sense the drop will be there, but the drop will be less when compared with AC. Okay, okay. So that's about the basic things about DC. Okay, now coming for this graph. So this is the rectified output. So this is also a DC. So throughout the time period, so there are certain cycles, half cycles are there, and we call it as ripples. We call it as ripples or rippled DC. Okay, so this is also accepted. So this is further classes will discuss why this output is being generated. So this is actually the rectified output. We are converting the while we are converting the power from one form to another form. So if the output is DC, so that DC will not be in this in these characteristics. So that DC will be rippled DC. Again, we go for stabilizer and we make the regulated DC like this. Okay. Next, coming for this single cell. So this is the symbol of the single cell, and if we go for multiple cells, suppose if we increase the, if you want to add the voltage sources, so then I can go for this series connection, so that the magnitude gets added, or suppose Vmax1, Vmax2. So these two can be added, and this is the another form. So you can write the polarities inside or outside of this circle. Okay, so polarities represents the direction as well as the type of supply here. So here DC voltage source. So suppose for example I write like this. How I need to consider whether it is a DC supply or AC supply? If you write the polarities like this, so then I can call it as DC source. At the same time, I can go for the direction of the current as well. Okay, or else the another form is you can write in this way. So this is also accepted. So this is how we are going to represent the DC. So I'm coming for this application. So I'm not highlighting the AC supply because majority of our loads are the AC supply, like any of the appliances. But whereas coming for the DC, so permanent magnet, separately excited, self-excited. So all these are comes under the application. Yes, all this comes under the applications. So here just I would like to highlight only this permanent magnet, which also we can call it as PMDC, permanent magnet DC motors right now. So for low power devices only we can limit this, otherwise we have to go for electromagnets. So I think nowhere we have discussed about this electromagnets. So what do you mean by these electromagnets? So first of all, before going for this electromagnets, just I'll give recall the fundamentals about this permanent magnet. So we know that if we consider a magnetic bar, let us consider here the north pole and this is the south pole. So the magnetic field will be created from north to south. So hope you remember all these diagrams. So you might be drawing a chart as well at the intermediate level. So this is the magnetic field. So this is the direction of magnetic lines of force. So this is the direction. This magnetic field is fixed here. So this magnetic field is fixed. Now coming for this electromagnet, so we need to create magnetic field. We need to create this magnetic field by using the electricity. So why we need to have this magnetic field which is created by electricity, in the sense to have this variable flux, right? So in order to have a variable flux, so for different appliances, so in order to meet the efficiency or in order to meet the requirements, we should have a variable magnetic field. So in order to create that variable magnetic field, we can use these electromagnets. So what do you mean by electromagnets? So the magnetic field created by electricity. How it is being created? So just we need to consider any conducting or semiconducting material. So just we are going to supply, let us see like this. Sorry, let me have some other diagram. So if you observe this, this is considered as winding. Okay, so this will be the conducting material. So let us consider for time being, let us consider it as an iron or some other bolt. Okay, so some iron bolt. I have used a copper winding here, and I'm going to supply a voltage. So since the circuit is closed, the current will be drawn here, and it acts as a magnet, and it is going to create a magnetic field. So hence I can call it as a electromagnetic field is created, EMF is created. Okay, so that's about EMF and permanent magnetic field. So these applications one by one we can discuss later. It just depends upon the type of winding. So if the winding gets changed, obviously the motor application also changes. So accordingly, these names are labeled here. So that is shunt motor, series, compound, long shunt, and short shunt. Right. Yeah. So the other thing. So already I have discussed this DC behavior and AC. So let us see this DC already have covered. Coming for this AC. Okay, so this is a direct component and this is an alternating component. Again, you might be having a doubt that alternating doesn't mean that only the sinusoidal will be there. So it can be a triangular waveform, it can be a sawtooth waveform, it can be a square waveform. All these comes under the alternating component. But out of all this, we are going to have only the sinusoidal. So that is why most of the supplies they used to have the symbol. So like this. So AC waveform, alternating current will be there. So okay, okay. So coming for this AC, so this is one cycle, so which I can call it as positive half cycle, and this which will be from G. Let us consider it is started from 0 and it is started up to 180 degrees, and this is 360 degrees. One complete cycle. What is called one complete cycle? One positive half cycle plus one negative gives the one complete cycle, which is 360 degrees. Okay, so positive half cycle appears to be at 180 degrees, and negative half cycle can be at 180 degrees. So total 360 degrees. So the up to 160, sorry, yes, let me change this color. Yes, so this is half cycle and this is another half, and this is another half. So the total gives one complete cycle. Okay, so this is the time period. X-axis represents the time period. It may be seconds or milliseconds or radians per second also, and the y-axis represents the voltage magnitude. So if you observe here the sinusoidal waveform, so the maximum voltage appears at 90 degrees. Either it may be a positive half cycle or negative half cycle. So because it is an the magnitude is in opposite direction, so obviously it is negative. So let us consider this is plus Vmax and this is minus Vmax. Okay. So what are the observations here in this sinusoidal waveform? It is an alternating component. So and here it is a sinusoidal. Sinusoidal in the sense it has only one maximum, one maximum voltage. I mean the maximum voltage appears at one particular point, that is 90 degrees. Either it may be a positive half cycle or either it may be at negative half cycle. So combination of positive half cycle and negative half cycle gives the complete cycle. So this is for single phase. Okay. So again, so what do you mean by phase? PHASE. What do you mean by phase? So phase is nothing but, see, in case of alternating component only we are calling it as single phase or three phase, right? So what do you mean by phase? Any signal changes its magnitude with respect to time, I can call it as a phase. Or the other meaning in the sense, a rotating vector is also called as a phase. What do you mean by a rotating vector? So any signal changes its magnitude. So this is the magnitude. Y-axis represents the magnitude. See, let us consider. Yes. See, if you look at this, so this is 45 degrees. This is 90. Again, this is 130. Yeah, 90 plus 45, 135, and it is around 180. Okay, so like this, up to 180 or 1 up to 360. Okay, so continuously the magnitude is getting increased here. Slowly it starts from 0, so it goes up to maximum. Again it starts from maximum to 0, and in opposite direction 0, again it reaches to maximum, again slowly it reaches to 0. So continuously the magnitude of the voltage, I mean the voltage magnitude gets changed with respect to time, and the cycle is continued. Okay, so we know that frequency is directly proportional to 1 by time period, or frequency is inversely proportional to time period. Okay, if the time period is getting increased, the frequency reduces, or if the time period is getting reduced, the frequency increases. So we know that the Indian standard frequency is 50 hertz. So accordingly the cycles will be there. Okay, so that's about alternating component. So here I have given some of the points already I have covered. Okay, so before this, I would like to give what is the reason of sinusoidal generation instead of a square waveform, or instead of a sawtooth, or instead of some other waveform. Why we are having only the sinusoidal waveform? So this is two permanent magnets are there. So this is the north pole and this is the south pole. So just consider a coil. So like this, just consider a coil. So these are the two ends. Let us consider P and S. Okay, P, Q, R, S. So this is the position. Okay, so initially we know that the magnetic field travels from north pole to south pole. So like this. Okay, okay. So north to south. So when this conductor is placed, we can call it this as a conductor. So when this conductor is placed in this magnetic field, actually it should be a varying magnetic field. So that is also important there. It should be a varying magnetic field. So when the conductor is placed in this varying magnetic field, what happens? It starts rotating there. It starts deflecting, and an EMF will be developed. Okay, so EMF is nothing but the voltage there. Okay, so just forget about this voltage development, how much magnitude of voltage is developed. So I'm not discussing right now. At the time of Faraday's laws of electromagnetic induction, I can explain you in detail. But as of now, we need to understand why the sinusoidal waveform is developed. So because of this rotation, what happens? So it is in phase with the magnetic field. So that is why the voltage is 0. Then what about the next position? It will be 90 degrees. The position will be 90 degrees. So now it has been shifted to C. Earlier it was PQ to RS. So now the direction, like it comes to this direction. So this is the direction. It will be perpendicular. Okay. So the red color will be in this position. Okay. So the magnitude will be maximum. Okay, it is going to deflect maximum. Again it falls to this position, so it will be 180 degrees. So at 180 degrees the induced voltage will be reducing. Okay, and it comes to 0. Okay, and in opposite direction now the position becomes, so like this. So P, Q, R, S. So opposite. Okay, so exactly. So this will be the direction. This is for plus 90 degrees I'm telling you, and this is for minus 90 degrees. Okay, now the magnitude is maximum in opposite direction. So that is why it is minus Vmax, and here it is plus Vmax. Okay, so this is how a sinusoidal waveform is developed because of the rotation of the coil. Okay, so hence a smooth sinusoidal waveform is developed here. Okay, and how the EMF is developed and what is the magnitude and all we'll see later. Just I'm giving the intro part of why the sinusoidal is being preferred. Okay, so for this only we can get the maximum voltage out of all the signals. So that is the reason we go for this sinusoidal. Okay, next. So I hope we can stop this discussion right now. So in the next class, we'll be discussing about this real, reactive, and apparent power. So this is one of the interesting and important topic. So we'll stop our discussion now.